have shared this class with you guys. I went to school a few years ago. I finished school in 2006, but I always have the best memories about going to school and learning things, and all the stuff that you're going to learn during your career is gonna go with you your whole life. So I'm hoping that you guys picked engineering because that's something that you're passionate about and something that is going to help you grow professionally and personally. I'm very honored to be here tonight. I'm gonna try to make this presentation as entertaining and as easy to follow as much as I can, so that you guys don't fall asleep in the middle of the class. There's probably gonna be a pop quiz at the end, so please pay attention. Um, so first, Islam asked me to come to this class today. So the topic for today is the design of pre-stressed concrete girders using precast pre-stressed concrete. And so I basically prepared um, a quick slideshow that tries to be more illustrative, so you guys can kind of see how things are designed hands-on in the industry versus what we might be doing, uh, in school in a more of a theoretical context. But I think, to me, it's important to go through the whole exercise of learning at school, all the theory behind it, because once you're in industry, you're basically going to be applying all your knowledge that you learn in college. You're going to be applying that to be able to, design a bridge. I remember when I took pre-stressed concrete class, we spent a whole semester designing just one girder, one precast pre-stressed concrete beam, and we use a lot of hand calculations and we use different programs. And in real life, you'll have a bridge and probably have about 80 girders or more to design, and that will have to happen in a matter of weeks instead of months. And so it is important to know the basics, but it is also important to apply that basic knowledge to be able to move fast and do a design that's good, that's cost efficient, that's constructible, and that can meet the budget. So the outline that I came up with today is, first I want to do a quick introduction, and then we're gonna have. I'm kind of hoping that um, you know, even though this class is virtual, I'm hoping that we can make it as interactive as possible. But on the second section of this class, I'm gonna just kind of throw some questions out there, and feel free to either you can write in the chat your comments, or you can just go ahead and speak up and provide a response to some of those questions. But the next one is, we're gonna go over one of the projects. So tonight I just wanted to basically pick an actual project that I worked on a few years ago in Washington State. And so the example that I'm going to be giving you is a bridge that's already open to the public. He opened a couple years ago, and basically it is a project where we applied all the knowledge from pre-stressed concrete and doing kind of getting creative with layouts and getting creative with design to come up with an actual final product. It's a nice bridge. Then once I kind of go over that project, I'm just gonna go through explaining a little bit how I designed this precast pre-stressed concrete girder bridge using a program that's called PG Super, and then I'll just open up for questions and answers. And so, so basically, I just wanted to do a quick introduction of myself. Um, so my name is Santiago Aguilar. I'm right now I work as an assistant vice president and on the structural engineering field for WSP USA. I was originally born and raised in Quito, Ecuador. Ecuador is in South America between Colombia and Peru on the Pacific coast. It's a small country, but it's a beautiful little paradise in the middle of South America, and I lived there until I was 18 years old. Then in year 99, after I turned 18 years old, I came to Northern Michigan, and I was an exchange student over there. So I went to high school. I did my senior year of high school in Manistic, Michigan, right off the coast, the northern coast of Lake Michigan, and I was class of 2000. Then after that, everybody in Michigan told me that the best school for engineering in Michigan was Michigan Tech University. So I apply. I went to community college for a couple years after school, and then after that, I got a scholarship at Michigan Tech, and so I went up to the Keweenaw Peninsula in northern Michigan to pursue my bachelor's and master's degree in civil and structural engineering. And I was basically just following my dad's footsteps. He's also an engineer in Ecuador. He's a civil engineer over there. And I think from as long as I can remember, I was like playing with dirt, and I like building things. And I think for me it was just a call from when I was a kid. I was like building things, and I was always around, heavy equipment and on all the things. So it was for me it was just a natural choice to go for civil engineering. So basically, I finished school in 2006, and ever since then, I've been basically working in a lot of different variety of projects, mostly focused on bridge design, and then also once in a while we'll get involved with waterfront structures, transport in general, transportation structures, walls, tunnels, railroad structures, grade separations, and so on and so forth. Right now, for the last 6 years, we've been we moved to Raleigh, North Carolina. And from the office in Raleigh, North Carolina, I've been supporting projects in the Southeast, so like North Carolina, South Carolina, Virginia, Florida. But I'm also involved in some projects in California and Washington State. And so I've been just kind of keeping myself involved in all kinds of different things. The company that I work for does projects nationwide, so for sure um, uh, it's for sure we always get involved in all kinds of different things. It's always good to have a variety of projects because that way you're familiar with the way that bridge design occurs with different standards, different codes at different states. I wanted to show a picture of my family. I guess for me, my why I do this is my family. I have three little kids that are growing pretty fast, and they happen to they gave me. I'm kind of right now getting over a cold. I'm recovering from that. If my kids take like 2 days to recover from a cold, it takes me about 2 3 weeks to recover from that same cold. But um, I I'm very happy to be in this country with all the opportunities, and I think a lot of other people are kind of basically like me, on the pursuit of happiness. And so for me, it's just it's a great happiness just to be able to fulfill my dreams here and do all the designs and be involved in a lot of big projects. Anyways, so that's that's just kind of the introduction. So moving on, basically, I just wanted to do a quick, but I gotta pick your brain session here. And like we are all learning, we're all going to school, we're learning, and obviously, like when you're going to school, there's to me, I feel that there's never stupid questions or there's never stupid comments. This is the time to learn. This is the time to make mistakes. And so, I guess right now, if any of you wants to chime in, but I got some few different questions here. For doing a bridge, that then basically kind of the two main prevailing materials that are used for bridges is either concrete or steel. You also have timber materials, you have composite materials, but normally the two materials that are cost efficient that can actually span long lengths are steel and concrete. But I guess can anybody tell me why we would use either steel versus concrete, concrete versus steel. What's one? I guess what's one of the big limitations, say, of concrete, or why would we use steel versus concrete or concrete versus steel? I don't know if anybody wants to chime in. Yeah. So Chandor is saying constructability. That's right. Um, Anybody else wants to chime in and basically say why we would use steel versus concrete? Yeah. So there's weather. Um, Somebody else said, yeah, cost. That's right. Thank you, William. Yeah, those are all the right answers there. So basically, the flexibility of construction. Yep, that's another one. That's very good. I think when you go driving on the highway and you see some bridges are steel, some bridges are concrete. I think in general, right now concrete is becoming a very versatile material, and right now we're kind of getting advancing in technology, and we're getting bigger, better materials and stronger materials. Now we can get concrete that are uh, probably over 20,000 psi compressive strength versus the typical 12, 15,000 that you use for precast pre-stressed girders. Um, yeah, maintenance requirement. That's another one. But I guess what I've seen myself with design of pre-stressed concrete versus steel is that normally when we're talking spans over 200 feet long, then at that point we normally switch to steel just because the concrete itself does have a limitation right now with the materials that we use in the United States. We have a limitation. Anytime you go up like you know or past 180 foot, 180 feet, then we're kind of talking more efficient use of steel versus concrete. But that's only a matter of time. I think right now, if you guys are able to investigate a little bit more about ultra high performance concrete, that concrete gets to be a very, very, very high compressive strength, and those materials are able to push the limits even farther. um, and so, and I guess the other limitation too is with steel versus concrete is like a lot of bridges out there that are like say on interchanges have very tight radiuses. So you have like some very tight radiuses and like curved the need of curved bridges or curved girders. So when you have a very curved girder or beam that you need on your bridge, then normally you have to switch to steel because steel allows you to have very tight radiuses. But so that's one question there. Thank you for all the answers there. And then the second question is why? I mean, why do we bother doing design? I guess. I mean, couldn't we just throw some big girders and bridge over a river and be done? Or like, why do we have to do design? I mean, why do we use engineers to design a bridge? And then again, like, please chime in. Yeah, safety is one of them. That's right. Lower cost. That's one big one. That's right. Thank you, Constance. Geographic location to maximize loading. Those are all good ones. Um, we do design because everything is expensive. Everything costs money. So normally when you we're working on a project on a bridge project, the owner normally is the DOT, the state DOT, or the county or the city. So they will normally give you a budget and they'll say, well, we have $40 million for this project, and that will include all the civil stuff, all the development, all the structural, and all the other disciplines. And so we always have a limited amount of money to come up with a design. So, and that's why we normally have to push the envelope, right? So we normally have to pick girders that are not too big or too small. We don't want stuff to be too small because we need to have enough capacity to be able to handle all the loads. But at the same time, we don't want to oversize our girders because then the project that we only had $40 million for, then we're gonna go over budget. Projects can very quickly become a 45-50 million dollar project, and at that point that would kill the project. So that's the reason we do design, like, at least for superstructure design, we normally design all the structure to be within the elastic range. But say when we're doing design of the substructure in some seismic areas, we design we design the superstructure, the substructure for some inelastic deformation, and for some tolerable inelastic deformation. But when it comes to superstructure, we're basically designing for the structure to remain elastic for all the service loads that we are designing for. The third question is, what do you guys think is the advantage of using a pre-stressed concrete beam versus a cast in place beam? And again, I need you guys to chime in. What? Yeah. So more constructible, higher quality control, less waiting time to set, time to construct. Yeah. So That's all correct answers. So pre-stressed concrete normally, pre-stress pre-stress will be made beforehand into. I couldn't read the rest of it, but um, basically, uh, the this yeah, it's more economic. That's right. And basically, yeah, large spans. That's correct. And so the pre-stressed concrete normally is precast. So yeah, like you can basically build this in the shop. So you'll be able to like mass produce, a bunch of girders, and then you'll be able to eventually send them to the site. Versus when you have cast in place, you have formwork. You have to uh, place the formwork on site, and then you have to wait until the concrete cures. And then you gotta take the forms out. So in some applications, cast in place still is a good method. Like, for example, if we're post tensioning something, we have to do cast in place. But when we have those bread and butter highway bridges that are for the most part straight, not crazy skews, then pre-stressed concrete is the way to go. So one way is, yeah, like the constructability and the schedule is improved when you're using pre-stressed concrete. But the other one is, I guess, the fundamental difference between the two is that with the pre-stressed concrete, we're actually inducing some internal loading, some pre-stress on the concrete beam by adding pre-stressing tendons or pre-stressing strands. And I'll kind of just go over that really quick on the next few slides. But we're basically inducing this internal loading on our system to be able to handle more loads, more vertical loads, more gravity loads. And so we basically, with the use of pre-stressed concrete, we're using a technology that is not that new anymore, but we're introducing the use of steel, of pre-stressed steel, to induce an additional load upwards on the system so that we can handle more load versus cast in place concrete. In cast in place concrete, we're relying mostly on the rebar that's normally near the tensile phase of the concrete to be able to handle all the tensile stresses induced on the concrete due to the different types of loads. And then we're relying on the concrete for the compression block on the compressive area of our beam. But if I compare, 72-inch precast pre-stressed girder versus a 72-inch cast in place girder, the capacity of a pre-stressed concrete will be, 50-60% higher than on the cast in place concrete beam, just because we have that extra component with the pre-stress. The next question is, so, I mean, why is it important to, I don't know, design by hand or use computer software? I guess why why do we want to do a hand calculation before we use a program? Or why should you guys do, when you take your pre-stressed concrete class, why should you go through a design by hand of a pre-stressed girder versus just going and using a program? So yeah, so to understand the basics, yeah, to verify that the software is correct. Yeah, those are really good answers for comparison and ensuring it's correct. Yes, that's right. Anybody else? I have a drink of water here. All right, so yeah, so basically that is the thing that people say: garbage in, garbage out. Um, yeah, to rule out garbage outputs from software. That's right. That's what I just said. So we first need to make sense of what is this thing doing? What's this program doing? And if the program is giving us right answers or it's giving us something that's way off. And a lot of times, when we get immersed in doing calculations, doing design, looking at numbers, sometimes we kind of get very limited vision on what's being actually calculated. So a lot of times, it's just good to take some steps back and ask yourselves, I mean, does this result make any sense? In a lot of times, on many instances when I was doing design, I would always come up with my first try, like using a program, I would get some really bogus, really absurd answers that didn't make any sense. And a lot of times we want to rely on that because we say, well, this is a program that that probably does the thing right. But we need to be able to verify that by doing some sort of hand calculation. So with pre-stress girders, when you guys take that class, or if you guys have taken a class, for example, you're able to easily verify your stresses, right? So you can take a section at mid-span, you can come up with your moments due to dead loads and superimposed loads and all that. And then you can at least get an idea of making sure that the program is reporting the right stresses on the girder, at least on the initial stages of construction, and just to make sure that the program is giving you is giving you some correct answers there. So it is always important to do some sort of hand calculation to check that your design using software is still correct. And the hand calculation part, through you're going to learn through going through the class and learning the basics and learning where stuff is coming from. And so it is extremely important that way. Um, so oops, I went to the next slide here, but so can somebody tell me what the design life requirement of a bridge is per AASHTO decode? What does the DOT or AASHTO requires to be the lifespan of a bridge? Anybody? For how many years do we design a bridge to last without major reconstruction? Yep. John said 75 years. Yep. Garrett, 75 years. That's right. Yep. So 75 years. Always remember that number. So the basic requirement for design for the lifespan of a bridge is 75 years. Now, those 75 years could become longer years if you have some robust maintenance program done to that bridge, or some clients nowadays some owners will require, 100-year design life for a bridge, but the standard is 75 years. So when you guys become engineers and when you guys start stamping bridge plans, you are on the hook for 75 years. So that means that the work that you do needs to be done in a very professional manner, to the best of your ability, and always asking questions to your colleagues and working as a team to make sure that your design is done correctly and everything that you have done is either checked by somebody else or is verified by a peer review or checked by a colleague of yours. But we always got to make sure that those designs that are out there that are there for over 75 years will be good for 75 years. So it might be, beyond our lifespan or our own lifespan, but a lot of those bridges out there will have either your initials on the drawings, or they will have your stamps, your PE stamp on the drawing. So it's very important that when you do a design, you take the time to do things right. And the things that I do myself is I normally compare my designs to like similar bridges that I've done in the past. And as you build up your experience, you kind of get a good feel for I don't know, for number of strands, for concrete strengths, for size of girders, all that kind of thing. So, what do you guys think that the future holds for bridge design or for bridges? Like what kind of innovative materials have you guys heard about in this last few years? Or what do you think, or how do you guys think that the design of bridges is going to change in the future, or what's coming up? Anybody? I did mention one innovation, ever FRC. Yeah, that's one. Anybody else? Any other technology that you guys have heard about? Plastic fiber recycled material. Yep. Uh, anybody else? Better ways to monitor service bridges in general. Self-healing concrete. Yep. Yeah. So I think there is a lot of talk about using composite materials, using recycled materials, um, improving on the current steel designs. But at least in the world of concrete, there is a lot of exciting things coming up, and I think some of those, the self-healing concrete using steel fibers or using glass fiber, um, reinforcing on the concrete. Those are all very exciting things. But one of the things that I mentioned previously was the ultra high performance concrete. Like currently, Lafarge is the company that has proprietorship on these ultra high performance concrete, and this is like very runny concrete, like no slump on this concrete. It's very like like soupy concrete, but it can get up to 25,000, 30,000 psi. And I know like FHWA is basically designing um, some some beams that are going to accommodate the strength of these beams better. So kind of guessing that in the future we'll probably see concrete spanning as much as steel, and concrete also being used for curved spans and for all these really cool geometry, and more importantly, having structures that are going to last more than 75 years. All right, so let's move on to the next thing here. Project overview. So I'm basically gonna go over an actual design that I did a few years ago. So I did the design of this guy that you can see on this picture. This is a Duportel Steel Street Bridge in Richland, Washington, in Southeast Washington. This bridge was designed, I designed this bridge in 2018, 2019, and this guy opened to traffic in December 16th, 2020. By the time this bridge opened, I had already moved to Raleigh, so I didn't get to see, I was not involved in the construction of this bridge, but I was very involved in the design from beginning to end. So it was really nice to hear from my colleagues that the project had been open back in 2020. This is this is a bridge that spans over the Yakima River in eastern Washington, and the city of Richland has some very specific aesthetic requirements with the concrete. Like you can see that the actual concrete girders were painted, uh, and the color that was selected for these girders was basically kind of resembling weathered steel, and that's just the way that they wanted to have the look on the bridge. They also had some features on the traffic barriers on the outside faces of the barriers. Um, and so these features basically were just part of all the architectural requirements just to have that aesthetic look to the bridge. And the eastern part of Washington State is dry. It's more like kind of like the desert over there. So then they wanted basically that bridge to have that look, kind of having more that earthy kind of look to it. And from this perspective, um, this bridge, uh, it kind of makes a kind of blend in with actual colors of the landscape and the location over there. So this guy was 772 foot long. It had five spans, and then it was 74 foot wide. It had four driving lanes. It did have sidewalks on both sides and bike lanes. On this guy, we use 10 lines of girders spaced at about 7 foot two. We use 83-inch in height WF83G girders. The WF83G girders are a Washington DOT standard girder. And those, if you just do the quick math here, we're designing 50 girders. And all 50 girders might have slightly different load requirements. So you will have, different designs to do. And this, I think, we probably had to complete the superstructure design in probably about maybe like in about 2 months. But the superstructure design, once you have the girders designed, then you have to design the deck on top, the concrete deck on top. Sometimes it requires some design of the barriers on top of the deck, the expansion joints, bearings underneath the girders, all these things. So there's all these different components that you actually have to design on the superstructure. So because this bridge wasn't this is not really that long, but it's pretty average length. We only needed just to use some large strip steel expansion joints, and the strip steel expansion joint is just no more than having these little kind of I beams, and in between the I beams you have these rubber glands that are vulcanized together with the little beams, and that allows for the bridge to expand and contract. And the whole objective of an expansion joint is to maintain the joint watertight so that we don't have water spilling underneath the bridge and potentially corroding the bearings where the girders are sitting on. So normally, like the objective of the expansion joint is to maintain the joint as watertight as possible. In real life, that doesn't occur so much because water always finds its way, but at least minimizes the the impact of having water spilling underneath the bridge, underneath down to the bearings. And also it helps drainage, right? Because depending on the slope of the bridge, you still have to drain the water away from the bridge to some location, to some catch basin. So in this case, we had PTFE sliding bearings on both ends of the bridge, and then we also had some large utilities underneath the bridge deck. And so that's basically a plan view of the bridge. This, what you can see here, black and white, is basically a typical plan view of a bridge where you can see, the span arrangement. You can kind of see like around like bend number three, that you have these scenic views that we had to add to the um, to the bridge because this area is very pedestrian friendly. So then we had bikes going across the bridge. We got pedestrian going across. So then we had these little balconies that we had to add. We had all those specific requirements on this bridge. Um, I guess going back to this, the other thing that you can see here is that this had a vertical curve, a horizontal curve. So the horizontal curve, we were in some radius the data for that radius is up on the upper right corner of this graph. But it was, I believe it says 1,880 foot radius that you have to be. So you have a horizontal curve. So when you guys took your your transportation class or your geometric design class, you went over, horizontal curves. The horizontal curves are normally basically following a circle that has some specific radius. So that's that. But then if we look at the profile of this guy, kind of going from the start of the project to the end, we're kind of having some pretty aggressive slope. Um, I don't remember what the exact number was, but I'm kind of guessing this was, in the order of like 5% or so slope. And so because of that, we have a drainage challenge, we have a geometric challenge because we have a bridge that's doing both horizontal and vertical curves. When you guys took the class, I guess just to make sure everybody's like still awake here, what shape do we normally use for vertical curves on highways and roadways? What conic shape do we use? Yeah, Walter is saying parabola. That's right. Can you tell me why we use parabolas instead of circles for geometric design for vertical profile? Why do we use parabolas instead of circles? Anybody? Okay, Walter was very, very honest, and he's saying that he doesn't know. Yeah, and parental next grades are often different. Yeah, I mean, yeah, those are some. Yeah, so the parabola allows you to, like somebody said, is allows you to control the exiting grade and the entering the exiting grade, and then you can feed some sort of parabola in between two tangents, but also the side distance. The side you can get more side distance with a parabola versus a circle, and so geometrically somebody determined that basically using a parabola is a safer shape than using a circle. So by the exiting and entering grade is a good reason, and also just being able to get more side distance from using a parabola. Basically, this typical section shows you some of the complexities that we have, but really to me, this was a bread and butter kind of bridge, very typical. And anytime that you encounter this kind of geometry, you'll probably be using precast pre-stressed concrete. um, and so, and here you can see, we have 10 lines of girders, and then we have, sidewalks on both sides. We have barriers on both sides. We have railing on top of the barriers, pedestrian railing. This had 4 lanes, but well, I guess some of the extra stuff that we had all these utilities going from one side of the river to the other. So we had water, we got sewer, we had fiber optic, and so we had like some additional loading conditions um, to basically consider in the design. And basically, anytime that you're kind of going over all the loads that you're going to have to design for, you have to take into account all of this. So normally you're either the civil engineer or the electrical engineer will at least tell you, okay, so this pipe weighs about 500 pounds per linear foot or 400 pounds per linear foot. So then basically we are, adding that extra loading on some of these girder lines to make sure that those girders are able to handle all the load, dead loads and live loads and superimposed loads. And the same, when we have these barriers, normally the weight of that barrier gets distributed evenly between the 2 or 3 external girders. And so that's how you would normally do it. Can somebody tell me, in a framing plan, we normally have these either concrete panels or we have the like steel shapes that connect two girders kind of together. What is the name of that? Can anybody tell me what's the name of that? I mean, those are not shown here, but bracing, yeah, that's when we're talking steel gear, that's bracing. When it comes to concrete, diaphragms, that's right, cross frame diaphragm. So Kyle said diaphragm. So yeah, to me, the correct answer for concrete is diaphragm. Um, so the diaphragms would normally go, underneath the bridge. And can anybody tell me what the objective of a diaphragm is? So like say I'm looking at my bridging plan. I don't know if I have a picture of the bridging plan, but like I have some girders that are in plan placed in such manner, but then I have these diaphragms that kind of cross, and maybe like in any given span, I have have these girders here. So these diaphragms. What's the main objective of a diaphragm? Anybody, take a guess. Integrated resistance against lateral supports, lateral forces. Yeah, yeah. So basically, what it is going back to my typical section. What the diaphragms do is like if I apply some big load on top of the bridge, what the diaphragm do is it makes that load being shared almost equally between all these girders. So basically, when I have girder, then I have a diaphragm on top, and then I have the no, I have a deck on top, and I have the diaphragm like here. It makes all this system to behave as one big beam. So this here is behaving as one big beam here. I have this deck, I have the diaphragm, I have the girder, and I have all this system that's basically trying to share all the load together so that we don't have only two girders doing most of the work and the rest not doing as much of the work. So that the diaphragms basically spread the load more evenly and make the whole system stiffer so that you can share the load better from one girder to the other when you have, some axles just on this side and you have some barriers on this other side, that kind of thing. So that's what the diaphragm does. Some other special requirements here was these, scenic views that I told you, and this is a kind of good picture showing these balconies. So these balconies we kind of had to include in our design for extra loading on the bends, like on the intermediate bends as well as the girders. um, this is a typical sheet for a pre-stressed girder. So you have basically an I-beam that's concrete. You have a system of both deflected or harped strands that you can see here. So you have a group of strands that kind of go like this, kind of like what you have here. And then you have a group of straight strands that run under here. And so the basic principle of pre-stressed concrete is that you're going to set the forms. So you have those steel forms in form of an I-shaped girder, and then you're gonna place your strands at using the design and the shape that you need to design for. And then you're gonna jack the strands, you're gonna pull on these strands, and the moment that you do that, you're gonna have these kind of hold down points here that are gonna keep my harp strands in position. And also I'm gonna jack my straight strands at the same time. And so that's gonna induce some tensile load, right? And when I have that tensile load, what this thing is gonna wanna do is gonna straighten out. So it's gonna wanna push the system upwards. So then once that happens, I lock the system in place. I place concrete. I let the concrete cure. Normally, most precasters will only make the concrete cure for about 12 to 16 hours. And then after that, once we get enough concrete strength, then we take the forms out and then we'll release the strands. When we release the strands, what will happen is this upward this upward load, internal load, is gonna push the system upward. So you're gonna get some camber on my beam. So my beam is probably gonna camber up 2-3 inches, and then as I apply load to my girder, then this girder is gonna straighten out again. But we're gonna have different stress conditions, different situations. So um, we have some miles still because we still gotta cover our faces of concrete for temperature and shrinkage. Still, we're gonna still gotta have some reinforcement to that, and then we gotta have some stirrups. So can anybody tell me what the stirrups are for normally? on beams for what force? What kind of capacity that does an stirrup give me for what kind of beam display? There you go. So Walter says shear. Yeah, and somebody else there said shear too. So that's right, shear. But also in pre-stressed concrete, because we have, especially when you have drape strands and straight strands, we're gonna have some bursting and some splitting forces, and those splitting forces originate from having deflected strands and straight strands, and you have all these forces that come in this location, and the force is developing very quickly at the kind of near the support. So in addition to having enough shear reinforcement near the supports, and normally near the support you have more stirrups, then you're gonna have to make sure that you have enough there for shear and for bursting and for splitting. And so those are checks that the program that I'm gonna talk to you about has. So basically, like the picture on the left here kind of shows you like placeholders for where the strand would go, and the numbers basically indicate the sequence of placing these strands on jacking the strands. Normally, there's the fill is basically the fill sequence. So, and that's because we want to make sure that the forces are balanced from one side of the beam to the other. But normally, when these strands are jacked, they're all jacked at the same time. Some beams, especially in Washington State, they allow for the use of temporary strands. Temporary strands are actually located on the top of my top flange, and the objective of the temporary strands is to basically be able to like push these girders even further, where we have this crazy jacking force that's being caused by the strands that are down here, but then we place these other smaller number of strands here on top, and then this beam is temporarily gonna kind of stay all in compression, and that's just to basically to have this stress reserve, or this stress capacity. So when I place all my loads on top, I place my deck, I place my live loads, I place all these loads, then these temporary strands make me basically meet all the stress requirements temporarily until I place these loads, and then these loads are gonna make this whole system kind of get back into compression. Concrete is really good in compression, but it's really bad in tension. Concrete cannot really take a lot of tension, if any, but it is really good in compression. So normally we want the system to stay in compression. So this is kind of showing you that you could probably put about 45, 40, 46 strands total without counting the harp strands. The harp strands are kind of like all grouped in together here in the center of the section. And so it really allows for a lot of force. Can anybody tell me what this thing is here? This really long table? Take any guess. Anybody, what's this table here? I mean, you can just read the title on top of the. Yeah, Jack. Right, you're so right. So Jack is saying that this is a girder schedule, which the girder schedule is the final product of your design as engineers. When you design girders and you have, spend all this time um, getting the design of all the girders, in this case, 50 different girders, then we summarize all the results in this table. So this table tells you, or tells the contractor who is fabricating those girders, basically the recipe, right? So this then is basically given what the length of each one of those guys is, what reinforcing is going to have, how many strands, how many straight strands, how many harp strands, what the initial strength of concrete is. So I think on this girder we had, pretty high requirement of about 10.5 KSI strength in 3 days, or at release. I mean, release normally happens like even 16 hours after the concrete gets cast, but they use, like high strength concrete with sometimes with accelerants, just so that the concrete sets. And then the next day when the guys come back to work, they can strip the forms out. And then by the time they're like done stripping the forms, that happens up until like lunchtime. And then when the guys come back from lunchtime, then they release the strands, and that's the last thing they do before they go back home. By the time that happens, it's been about 16, 18 hours. They release the strands, and then the our girders just basically they have this camber. The camber is just an upward deflection of the beams due to that effect. So then this table basically tells them all the things they need to know to fabricate the girder. So this summarizes all of your um, requirements for making this girder. So going to there's many programs that you can use for designing girders. One of the ones that we use out west in Washington State and Texas and Kansas is PageSuper. PageSuper was developed by the Washington Department of Transportation and the Texas Department of Transportation. This is a pretty cool program, actually. If you guys want, you can download it for free. If you just Google WashDOT or WSDOT Bridge Link, it's a free download. It's public domain, but this program will teach you a lot about girder design. And so we like this program is fully accepted as an actual design tool in Washington and Texas. So we use this program for actual plans and designs and everything. And then there's other programs, there's PSBIM, there's LEAP, there's other programs that are used that are licensed programs that you have to pay money for, but this program is just as good as any of those other programs, and it's very reliable, and it gets updated, once or twice a year. So, but as we said before about the garbage in, garbage out, nothing can replace your own knowledge of the subject. So this program can give you some good results. It could probably give you some bad results if you don't put the right inputs in there. So always make sure that you have some sort of hand calculated answer in there, to verify your designs. So this is basically a quick view using PageSuper. And so this is the view of my same bridge that I designed here, but it's basically the model of it. So the top is just the framing plan, kind of showing each one of the bends, showing each one of the girders at each one of the spans. So we have maintenance of girders. The down here we have a typical section showing also all the girders with the deck, with the barrier, with the sidewalk, all the things. So normally, like the main parameters that go into here is with PageSuper, you can design, your geometry and layout. So, vertical curves, horizontal curves, all the things that the roadway that's part of where the bridge is going through. All bridges are basically part of the roadway, and because they're part of the roadway, they have to follow some sort of geometric design. So normally, the civil designers will give you the parameters, the vertical curve parameters, the horizontal curve parameters. Then there is some design charts that will tell you how far each girder size can span. In this case, because we were using spans over 100 feet, we use 83-inch girders. We could have probably used, 74-inch girders, but the 83s were a better fit because we have kind of higher loads on this bridge because of the utilities underneath and those balconies and the haunches and all the things. So basically, like we came up with, the 83-inch that was kind of more desirable. And then additional loads, into take into consideration. So we have, DC loads, so dead loads. We have DW loads, so superimposed loads, and then we got live loads. So in addition to all the loads that you model in PageSuper, you have to take into account the addition of superimposed loadings, which is my future wearing course, because you normally design the deck to eventually get resurfaced, and it gets, sometimes it gets asphalt on top, or it gets, additional concrete on top. So you have to design for future load on top of the deck. And then then once you come up with all the loads and you pull your loads in the model and you run the model, then you do basically some design checks. And the design checks are the stress at different stages. And normally for pre-stress beams, the stress checks is actually what control the design more than the moment capacity or the shear capacity. Or and then lastly, one of the important pieces of information is this estimating pre-stress losses and camber. when you take your precast, your pre-stressed concrete girder design class, you'll go over what losses are, and that's basically pre-stress losses. So when I'm jacking the strands, we normally lose some of that the effective stressing on the strands, and that has a incidence on how much my beam cumbers. So going through the different stresses on the beam at different stages and at different locations of the span, we normally we have to make sure that we have enough steel going through the system to stand all the basically all the different stresses, right? So like say this one is kind of already showing properties for a composite section that has a girder on top, but like say when I'm just releasing my strands, and my girder is just by itself with self load, you're gonna still probably gonna have some tension on top because my basically my concrete here is it's like deflecting upwards. So you have to make sure that stress that you have here, that extreme stress in tension that you have, is within tolerable limits. So just to make sure that the concrete doesn't crack, or to make sure that you have enough steel. And the same, as you go on different stages of the design, as you are like adding more load on the system, then that tension may disappear, right? You might have a beam that's kind of deflecting downwards, and then at that point you might have something where kind of what you're seeing here, where all like the top and the bottom are in compression, and then eventually, once you're applying all the loads, so dead loads, live loads, and everything else that you design for, then you might encounter some tension at the bottom. I mean, it's kind of exaggerated, right? But I'm applying this load, and my beam is maybe no, it's not gonna sag down, but it's gonna deflect downwards and potentially can just kind of level off. But at that point, the desirable outcome is that the whole system is in compression, or like down here, you basically get zero tension or a very, very small amount of tension. The the Washington DOT doesn't allow any tension on at the bottom at final conditions. So we normally always design for the system to be basically like this. So either very small, like no compression or tension, or very small, still in compression. And so, uh, so it's kind of the same, kind of reiterating the previous slide, but kind of making sure that we're checking the different stages of construction of the girder, and then we're following and making sure that we meet all the criteria for stresses. Now the next thing is checking moments and shears. And moments and shear normally doesn't control the design. Like normally, if you provide enough strands on your system to be able to overcome all the stress limitations, then normally you have enough moment capacity. And the same with the shear. Normally, if you just follow the standard detail from the DOT on the number of stirrups that you place, then normally the shear is met, but you still gotta check it. This is an illustration showing the basically the different stages in regards to camber. So this kind of saying, like I'm gonna cast my gear there, and then when I release my strands, my whole beam jacks up some amount. So basically you get some immediate camber up. So this number one is basically that immediate camber that you get from releasing the strands. And then as time goes by, the material creeps up, and the material continues to gain strength, but at the same time, the strands tend to continue to provide that pre-stressing force to the system. So the system continues to basically camber upwards. And then, like in this case, we cut the temporary strand we have up on top, and that increases the camber. And then once we cast the deck, then we basically the system kind of comes back down. And then as we continue to add loads, diaphragms, barriers, all the superimposed loads, the system eventually levels off. And then we have this number that's called screed camber. And this screed camber is basically we have a profile to follow, right? So we're gonna say at the end of the day, we're gonna follow this vertical profile, but we cast our deck slightly higher so that when the self weight of my deck and everything else makes the whole system come down, I end up at the basic, design elevation that's a little bit lower, following my vertical profile. And so right now, what I'm going to do is I'm gonna show you really fast. Let me see if I can share my PG Super here. All right. Can you guys see my? I don't know if Islam. Can you confirm that you can see my PG Super here?
Yes, I
Awesome.
can.
Yep. Very good. So yeah. So this is the program, right? So this is already kind of set up all the framing. So we have our 5 spans, different lengths, different locations, bearings. But this program basically, where you have, on the edit tab here, that's kind of like if you go just basically down this, you're gonna set up everything. So this first tab basically shows you, like this is the the vertical profile that we're gonna have on our bridge. So like say this one has an exit grade of 1.5 minus 1.5 percentage in the PBI station, what the initial elevation is, what the entering grade is, all these things. Then like this is defines the horizontal alignment of the bridge following this 1880 feet radius. And then here you basically can define your crown, right? What can anybody tell me what the crown is for mainly? That the 2%, the 2% slope um, that you can see on the typical section here. Yeah, yeah. So Hamdi said rain. Uh, so yeah, so that mainly is for drainage. So we want to make sure that we have this um, cross slope, making sure that when you get some rain event, that the roadway drains properly. And so um, and so basically that will help the whole drainage system. And so that's and then here on bridge, then you can basically specify your general layout. So for each bend, you will basically say what the stationing of each bend is, what the bearing is of each bridge, so what bearing is following, and then the location of each abutment. You would specify what kind of what kind of barrier you have on each side, um, and then basically like typical girder depths, like my main bridge deck depth is about 8 inches, but also you have a haunch. Does anybody know what a haunch is? It's called a haunch. All right, Constance, what can you explain briefly what a haunch is? Or yeah, the part between the girder and deck, right? And okay. Yeah, so the haunch is basically a portion of concrete that's on top of the girder, in between the girder and the deck. And that little leveling pad is basically to level off or to compensate any difference between my vertical curve and actually what path my girder is following. Because, my girder is not going to be following exactly what my vertical curve is doing, right? My girder is going to be cambering one way, and it's going to be following like more or less the same elevations as the vertical curve, but there's always going to be imperfections, right? Because while my vertical curve is following this big long parabola, my girders, my 5 spans of girders are basically following, just each span is following, its own camber. So you can probably predict that most times the haunch is greater at the location of the supports, and then it's the smallest one once you get to midspan, because at midspan you have the greatest camber, but that doesn't, that's not always the case. Sometimes we have bridges on sag curves instead of crest curves. And in that case, you can have the opposite, where you can have a bigger haunch at midspan and the smaller haunch at the support location. So and so basically, this program actually can also do design of your bridge deck. So like here, you can actually specify the reinforcement for your deck, and then you have other parameters that you can put in here. But on this, uh, you can basically specify. Let's see. On this, like say you can specify like what the span lengths are, what girders we're using. So here I'm saying we're gonna have 83-inch girders and all the things. And then these are basically the distances from the support locations to the actual bearing locations on the girders. You can connect with kind of basically this indicates what the location of the diaphragms are, what offsets you have. So you have to basically, the first part of this is specifying all the environmental geometry, all the different constraints that you have on your projects. Um, this is the haunch that we were talking about. But the Washington DOT normally uses the definition of the A dimension. The A dimension is the distance all the way from the top of the girder to the top of the deck. So this includes the thickness of the deck, that's 8 inches, and it includes the thickness of the haunch itself. So the thickness of the haunch, right now we're basically in some locations we're doing at Pier 2, we're using about 2.5 inches. In some other locations, we're going to 4.75. And at different locations, it just kind of varies. And the reason that happened is because in this case, because we have kind of like the bends are not skewed, but you have two things going on. You have the super elevation going on, and then you also have the vertical curve profile going on, and then you have the different offsets of the girders. So that just made the whole geometry of this thing way more complex. And so the whole objective of the haunch is, as long as your deck is at least 8 inches, then the haunch can get down to almost like zero, but you can never have a negative, or you can never have a location where the deck goes less than 8 inches, because just by design we need the 8 inches. We need enough strength on the deck for all the traffic to run through. So the haunch facilitates that irregularity that occurs, compensating between the vertical profile of my roadway or the bridge that's going through it, and then the actual position of the girder. So here you can see that we had to kind of play with all the haunch thicknesses all throughout the project. And so, once you establish all these different um, all these different parameters, like here you can kind of see, on this girder tab, you can kind of see what concrete release strength is. So here we had specified 7.5, 7.5 KSI for release strength, and then 10.5 KSI for final strength at 28 days. And so at each location, you can specify how many strands you have. So here I'm saying for this girder that's on span 1 and the girder A, which is the first girder all the way on the left side, we are using 22 strands, straight strands, and then 8 harp strands, and then 2 temporary strands. And so the problem, like normally the design is basically playing around with these numbers here. So you basically like play around with this 22, 8, and 2, and then the strength. Basically, those are kind of the main things. Now, normally the program will always assume that you're always jacking each strand at a percentage of the yielding point. So normally we'll jack at 80% of the yielding point. So then this already calculating what the jacking force is for each one of these strands. So normally you use 0.6-inch strands on each one of these strands. and that's what the levers end up jacking force to be able to overcome all the forces. But this kind of view of the beam with all the how many straight strands you have and how many sharp strands you have, and then you can also specify the longitudinal reinforcement for the girder. But this longitudinal reinforcement doesn't play much of a role for design. It's more just basically temperature still that you're putting on your girder. And then, but then here you're specifying your shear steel, so your stirrups, how many legs? Normally you have two legs, number 5 bars. So I guess what can anybody tell me why I normally don't want to use number 6 bars instead of number 5 bars? Anybody just take a guess or tell me why do you think I would prefer to use number 5 bars for the stirrups versus number 6? Yeah, so Abu says because the concrete pouring will be easier. That's right. Like if you can remember the plan that we looked with the stirrups, the standard plan, when you have near the location of the supports, you have these all these legs of stirrups. As in those areas, it just gets super congested. So normally we want to stick with our number 5s. You can do number 6s, but the precasters don't like that. If you show a plan with number 6 stirrups, you're gonna get a strong worded comment from the precaster. So and that's why one of the challenges in the design is making sure that that area doesn't gets all the strength that it needs to get, but also we don't want to be like putting a lot of big bars in there. So normally like we try to stick to number 5s. Anyways, so basically after you go through all of this work, there is this thing here that on view reports, and there's so many reports, right? But the only one that I normally pay attention to is this spec check report, and say, I want to check spec report for the span 2, girder B, and so this does a quick check, and then here it will tell you, like, it gives you a whole display of results. So here it's giving me some warnings because, there's some geometric warnings, which is fine. You normally get those. But then here it will tell you, like some of the stuff, what stuff was not met. So in this case, here's telling me that this fell on the lifting checks. So in addition to the design that we do for the girder being on a bridge with the loads and everything, the contractor normally is responsible for doing a temporary design, which means the contractor, when they're shipping this big concrete down the highway with two supports, and you're having, this, and you've seen this on the highway, where you have these big girders going, underneath the bridges, making sure that you don't hit any of the, like you meet all the clearances and all the radiuses on the, like when you're going around corners and all that, but also like making sure that that big girder doesn't tip over, also making sure that that girder is able to stand all the impact loads during traffic. So when you're moving this girder from point A to point B, you have some inherent um, impact loads due to traffic, right? So that this big truck hits a, a, a pothole, and that's an impact load. So then the girder has to be able to stand all those temporary stress conditions, and then also the contractor needs to be able to lift this concrete in place and basically just put it in place. And so then this program also does checks on that. But so like at the end, how I check that's um, uh, for lifting and that kind of thing. So you have to make sure that, or the contractor is responsible for designing the lifting hooks at the end of the girders to make sure that that concrete is going to spout out when they're like lifting the concrete. So they have to put, basically some bars around the hook inside the concrete, or some confinement spirals, just to make sure that that concrete is confined where the location of the lifting hooks are. So, but basically going back to this is gonna perform a check of stresses at different conditions. So like first, it's gonna perform a check on the stresses at jacking. So you're gonna have some compression, some tension. In this case, because we have temporary stress, you can see here that the top and the bottom fiber are both in compression. The bottom is in bigger compression than the top, which that makes sense. But then we have some checks for tension. So the same is kind of telling me that my system is at midspan is in all in compression. And so basically that's all the checks um, for stresses at different stages. But normally the one that I see that controls the design is this service tree tension. And service tree tension is when you already have all the loads in place. So you have your dead loads, your live loads, all the loads. And then at midspan, you're gonna kind of gotta make sure that your fiber on the top and at the bottom is either all in compression or this guy here has to be at least, well, here is like the limit is zero. So it's saying no tension, but it can be, you can have zero stress there. So if I would have put like a couple of strands less, this probably would have gone down to either zero or a positive number indicating that the bottom was under tension, which for Washington DOT is not allowed. So the reason they don't allow that is because they think or they believe that by doing that, by keeping the system all in compression, that you can actually improve uh, the durability of the girder just by keeping all the concrete basically less prone to cracking. So you can see that the first check is all about stresses. Then the next check is moment capacity. But I never find any issues with moment capacity. Like if you can make your stresses work, your moment normally works out fine too. And that's because when you're doing moment capacity, this is using the strands as your main tensile steel for capacity. So normally like there is different checks for strength for moment capacity at different stages, and then it comes the checks for shear. And so the same like the checks for shear, as long as you have your stirrups reasonably spaced, then basically you have this doing just fine. All of these factor of safety against failure and against rollover is normally the responsibility of the contractor, but this program still checks this. And normally when a contractor submits a shop drawing with the girders, they will have to do a check because they are the ones handling shipping and handling the girders, so they need to be the ones checking that kind of thing. We normally do the design when the girder is on site and is on the bridge, but anything in between, like from the moment the bridge is manufactured or the gear is manufactured to the moment it gets delivered, that's the responsibility of the contractor. So and so there's all kinds of different factors, but uh, with this, you basically have to check all 50 of these guys. So you basically have to generate 50 different reports, but normally the designs are similar, where like for any given span, you use the same design for the exterior girders versus the interior girders. Sometimes the exterior girders get a little more load because you have the barrier load on the exterior girders. Sometimes the interior girders might get more load because some of them have the utility loads that you guys saw in the typical section. So it just kind of depends, but kind of have to make sure that in all cases you basically meet all the loads. Um, and so, and then there's like different, I don't know, there's different checks you can do. So in this case, I'm basically showing you the stress distribution at the span 2 girder B, and that's kind of saying that at condition um, at service 3, we're having at service 3 we're basically having the whole system is in compression. So here you can see that my stress is negative for top fiber and bottom fiber. So to me, that's the desirable outcome that and you can develop plots for all spans or for just any given span. But there is all kinds of information that you can get from this. But obviously, like from the report that I showed you before, the spec check report, a lot of times you can, with your hand calculations, you can actually come up with these numbers here. So you should be able to like come up with these stresses, what is at release, because at release you know what the release strength of the concrete is, you know what the moment of inertia of your section is, You know what the jacking load is, you know what the eccentricity of the strand is. So, you know, this article you can check by hand, like all these initial stages that is easy to check. Even up to the point where you have live loads, you can still like, you can get the moments due to live loads and the moments due to dead loads, live loads, and then you can still come up with stresses to check to make sure these numbers are correct. So with that, let me go back to my other screen here. And so that's kind of you know, this might take to actually be to design a prestigious girder. It could take, you know, a few weeks. Try to summarize everything in about an hour. And I know you guys probably have a bunch of questions. So that was just an overview of PG Super. What I encourage you to do is to download the program and use it. And you can just use it. Like there's tutorials you can download in there. There's like already some files with actual bridge models that you can design. So you can like start with a simple span bridge, you know, and do a quick design with the deck and barriers and all that. But having experience using pre-stress girder design program is very important, and that'll help you find a job quick, because if an employer knows that you already know how to design a girder, they'll love it. I mean, I've spent 17 years of my life designing these things, and I know that I started designing girders right from my first year when I was was just fresh out of college. That was one of the first tasks they had me do, like design girders. So with that, I am going to open it for questions if anybody has any questions. And I don't know, like probably better if you want to use your microphone, or if you want to send me a quick text, or um, all right. So Hamdi, you have a question.
Yes, actually, I want to ask about you said the haunch, the girder haunch.
Yeah.
We may have different height of girder haunch for the
Yes.
start of the beam or the beam midspan. Is it a matter of geometry or something else?
Oh yeah. I mean, it's mainly geometry, and it's a combination of geometry of the girder and your camber. So, like, you know, a program like PG Super can actually calculate the difference in camber throughout the length of each girder, and it will estimate a reasonable thickness throughout to calculate dead load, because obviously the dead load of that haunch varies, right? So yeah, and it is an additional dead load you have to consider. But it's basically the fact that you have a difference between your, you know, your horizontal, your vertical roadway profile, and then whatever your haunch is doing in combination with if you have a skew, you have the gear there following, you know, you have the bend following a skew, you have the bend and the bearings following a specific skew in combination with vertical curve variability of the elevations and also the super elevation. So it is for sure a compensation between geometry and girder camber.
Yeah, I got it. Thank you.
So like on Pretty Super, you can pull out a report for camber, and that will actually tell you how much the the camber actually varies throughout the length of the girder. That was a good question, Hamdi. So anybody have any other questions? Come on, don't be shy. Ask a question. I don't know, Dr. Mantawi, if you have any questions for me.
Thank you very much. It's a very interesting presentation. I'm pretty sure that I don't know if you know or not, but the students are assigned to do several bridge design alternative based on 10 different states. So there is a 10 groups of 3 or 4 students, and they are working on different design spans and length, and they are assigned in 10 different states. Try to maybe check some bridge design manuals and use. I already covered with them the steel design using the leap steel, and maybe I will say half and half. Half are doing steel design and half are doing pre-stressed concrete design. So as it evolve next couple of weeks, I think the student will be able to come up with different design that we can compare.
Yeah, I mean, for sure, yeah, you can use that program to verify the results. I mean, Page Super is probably gonna do way more than what the project entitles, but it can certainly be used for verifying the results of the design. And obviously, you know, if I can be of any assistance on any stuff like that, you know, you can feel free to share my information with your students, and I'll be more than happy to. If anybody have any questions or anything, I'll be more than happy to help out.
That's great. Thank you very much for your time and information, and we'll stay in touch. So I'll send you the record too for your reference, and I'll stay for maybe 10-20 minutes with a student to just discuss the project, and we can adjourn the class today.
Okay,
Thank you.
sounds
Santiago.
great. Well,
Thank you.
thank you guys. Appreciate your time, and I'm happy to help you guys out today. Hopefully, the class was interesting enough, and yeah, feel
I'm
free
pretty
to
sure,
reach out if you have any more questions.
Thank you, Santiago.
Yeah.
So let me stop recording.